Yay!
It's receiving our content.
I believe
The stream
you.
is starting.
Hi, YouTube.
The stream is live.
Oh no. Cool. Well, this is neat. Huh?
Talking to the internet now.
Yeah, I am. What's up? Well, we've still got a couple of minutes, so YouTube's a little early.
Actually, it's 6:59.
Shocking.
And you have 10 seconds.
Saturday. 4 days. So I'm texting.
Is that just going to take pictures of Kyle's face directly?
How's I don't even know if
I can't see your previews though.
I just hope so.
Oh no, it's really close.
I'm like, well, we're gonna estimate $5
Please turn over to validate.
7 o'clock. You start this on time or what, Kyle?
yes we can. Well, it's 7 o'clock. Our misec meeting is ready to rock. If I have your attention, we will be starting in about 10 seconds, actually, right now. Not too many announcements going on besides that tomorrow, if you're in the Lansing area, we'll be having our first Lansing misec meetup. It'll be hosted by Tech Systems at the NAP building downtown at about 7 o'clock. So if you're in the Lansing area, definitely check it out. Otherwise, I'll just turn this right over to Daniel.
What's up? What's up, Kyle?
What do you?
Hi.
Hi. Hey. What would you say you're talking about today?
I'm going to be talking about, from a very beginner's level, how buffer overflow exploits work. That's what I'm going to be talking about. You got any more announcements, Kyle? We're good to go.
That was it. That's all I had.
All right.
No cat
So,
jokes?
hmm?
No cat jokes?
Well, not yet. Maybe later.
I'm not here.
That's a good point. We can't give him the satisfaction. Kyle's probably got plenty of his own. Yeah. Come on. Where's our pun, Kyle?
The opening pun, come on.
Pressure on the spot.
And now I got this.
It's unbelievable right now.
Don't do it.
You don't have it.
Oh man. I know you can do it, Kyle. He's trying, so I'm just going to wait for him to give us a
friend
pun.
of mine tried to annoy me with bird puns, but I soon realized that toucan played that game.
Toucan.
I got it, man. I got it.
Well, that's thoroughly demoralizing, but thank you, Kyle.
Welcome.
How's it going? Glad you could make it.
Rip rap.
All right, so last time I did a talk, I did a very basic introduction on how debuggers work. Today we're going to be using Debugger a lot, so we're going to see a little more of that. Also, when I first started programming and learning about variables and functions and stuff like that, I didn't know how the computer worked behind the scenes. I was always a little bit mystified, and then you learn how to use the debugger, and you start to see a little bit more. And then you learn how to take advantage of the computer. You learn how to make it crash. You learn how to make it do all kinds of crazy stuff. And I didn't know why it did any of that. And so I would have loved to see a talk like this when I was starting to learn programming. So that's why I'm here. So let's find a pen. Did we establish which one worked, Kyle?
Just make sure it's not a marker. It should on the side of it say dry erase.
No, it's just permanent.
It's beautiful. It says
English is not his first language.
it says dry erase. All right. So where we're going to start from is, let's see. I just hope everyone gets out of this talk what they want to get out of it. That's my only concern. As long as you know a little bit about programming, you should be good. So the first thing that I wanted to talk about is how's memory laid out when you run a program? How do variables get stored? Where do they get put? How does the compiler choose where to organize the variables that you assign? Because when you compile a program, the code that you wrote gets mangled up, and the behavior you want theoretically comes out. So the compiler has to decide where to put all of those variables in memory. So the first thing that we need to learn about, and I apologize if this is review, but review is always good, is the stack. The stack is where your function's local variables live. If you're in a function, you assign some variables, you reserve space for some variables somewhere, it's probably going to go on the stack. And we have to talk about how the stack is laid out, and then we can talk about how to take advantage of that layout to do crazy stuff. So, first of all, we call a new function, and the computer keeps track of a bunch of cool numbers. So, let's say this is the bottom of memory right here. And let's say this is the top of memory right here. All right. So we call a new function, we get a bunch of memory laid out for us. The first thing that happens when we call a function is, let's see, I'm going to skip a few details here, and we're going to miss out a couple of steps, but you're going to get the general idea, and it's going to be enough to carry on. So let me try and remember this. The first thing that happens is the previous frame pointer gets pushed onto the stack? Let's call that good enough. So right here, we start with our base pointer, which we're going to call BP, base pointer. And this is the same thing we'll see on the screen shortly. And we have another pointer called the stack pointer. The base pointer always keeps track of where your stack starts, and your stack always starts at the top address of memory, and it grows downwards to the 0 address. As you allocate more space for more variables, the stack pointer, which keeps track of where you've got to, will advance down. So the first thing that we do is let's see. So let's allocate some space right here for the old frame pointer. So all right. So we've just got a little bit of space right here. When we call our function, it has to remember where some of the previous details were. So it's going to remember a number right here. Let's see. This is the more interesting part. The second thing that happens when you call a function is the return address. This is the cool thing. This is what we're going to really learn about later. Where does it go after your function is done? That is stored right here, right at the top of memory, right next to the saved frame pointer right here. So as these things get allocated, this stack pointer will move down, so the computer knows how much memory you've got left. So what happens next? We've got a couple of things saved, but we've got a bunch of space. So now we can assign our locals. Now we can make space for our locals. And say you have a function that just assigns 10 bytes of space. There you go. You got it. There's your buffer. And we'll see an example of this later. So now, once we've made space for this gets moved again down here. So this is where we've got to. So this will always point at a lower address, and this will always point at a higher address. And the difference between these two is the space that you've got allocated, that the program knows about and that the program can play with. All right, so let's keep this in mind and move it all the way over here. All right, we'll refer back to this. So let's get to the cool stuff that I like, if I can figure out how to sign back in. If you'll excuse me. All right. So I wrote a bunch of example programs, and let's see how they work. OK. So we have a pretty simple program right here. We just have one function. We just have a main. We have a couple of buffers. And we copy some stuff in, ask me a question, do some stuff. Let's keep that over here. And let's put this over here. So let's run this program and see what happens. All right. Oh, okay. I got it. I got this. Yeah. Oh man. Okay. So we got some output. That's a little interesting. So let's go back over to the board for a second. So my input got allocated right in here, right? So what if, let's see, I can see that the name buffer is 10 bytes long, which means that I could put in up to 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we'll leave a space for the null byte, and it does the same thing. So at this point, we've filled up the buffer. So if we don't have any space now, right? We've got to the end of our buffer that's been allocated, and if we keep writing, it's going to keep writing from smaller addresses to larger addresses. So it's going to write towards the right on the diagram over there. Should we move this? Is this working out? I don't know. All right. It's going to be terrifying. Oh my god. All right, so it stands to reason that if I keep putting more stuff in, we're going to fly off the edge of the board. So let's try it. Let's see what happens. Oh my god. Oh my god. Oh my god. Reckon that's enough? Reckon? Okay, let's... Oh my god. Okay, so we've got a bunch of crazy output right there. This is confusing, and I don't know what's going on. So, let's load it in the debugger and see what happens. So first, let's look at our function. So we've got a bunch of crazy stuff. I see some things I recognize though. Here we've got our puts call, which is most likely correlated with this print right here when it asks for the input. We've got a call to gets right down here. This is probably where it asks me for my input. And then way down here we've got our call to the final print. So how do we see the memory? This is the program, but how do we see what it's actually storing in memory? Luckily, with the debugger, we can look at memory as well. So first, I've got to start running this program because we haven't started yet. So, whoa, that's not what I wanted to do at all. All right, so first we're going to set a breakpoint so that we can stop somewhere. And this address that I'm putting in is just the addresses from the left-hand side, so we can choose which line of code to stop on. And I am going to stop right after I've done my input. So I can see right here is where we get our input. Right here is the address afterwards, so let's stop right there. Let's see, F48, F20. Does that look right? All right. So let's see. I'm just going to put in a bunch of A's for now. How many did I put in? Did I put in enough? 1, 2, 3, 4, 5, 6, 7. That's probably enough. So I know that A is going to show up in memory as the hex number 61. So we're going to be able to see this in the memory dump. Pretty good. We hit our breakpoint. And we can see that we've got a little arrow showing where we are. So we need to see memory. So I talked about the base pointer and the stack pointer earlier. The base pointer keeps track of the highest part of memory. The stack pointer keeps track of where we are. So if we are going to output memory from low to high, we better output the stack pointer. So we can use GDB's examine command, or X, and we can output a bunch of memory. Let's see if I can remember how to do this. Let's do this. All right. Let's move this over a little bit.
Yeah.
Okay, I just wanted to let you guys know they have to have badges. They don't have to now, but we can't have unescorted guests.
Okay.
So when people are just kind of roaming in, if somebody could just wait for them next time and make sure.
Yeah, we will.
Alright, and if you have any problems, just call security. We're always there.
Okay.
Thank you.
All right, we all care about security, right? Exactly. You know, if you come to these talks, you can learn. Everything is fine. Okay, so let's move this over a little bit so we've got a little more room and it's a little clearer. Get over there. All right. So all we've done is we printed out a bunch of memory, starting from the stack pointer and going right on down there. We can see where those two things are pointing if we look at the registers right now. So right about here are two registers. Here's the stack pointer, and here's the base pointer. And we can see they're pretty close in memory, which makes sense. So where is our base pointer? To that address. So if we print our stack again, we should be able to identify where the base pointer is pointing to if we count. So I can see the base pointer is at 6A8. Here's 6A0, and each one of these chunks is a 4-byte word. So if this is 6A0, then this little chunk right here is going to be 6A4, 6A8. So it stands to reason that the base pointer is pointing right here. So let's confirm that. Whoops, let's try doing this properly. And that looks like the same number right here at 6A8, and it's right there. So our variables have to live between here and the top. So we can see that we've got a little bit of slack space because I can see my 61s right here and right there, which makes sense because I think did I put in 9 61s? So we've got 4 8 61s, and we've got our 9th one right there, and then right after it is our null byte. And I know things are a little backwards, we'll get to that in a minute. We've got some slack space because we don't allocate exactly how much memory we need because we're computers and we've got a bunch of memory, we can waste it all. That's not true. We've got to be very conservative. But we also have to allocate chunks at a time. So we did. So we've got some slack space. You can see we've got a bunch of zeros here. That's probably fine. But we can't access this region right now. We've got to start right here. This is where it starts our input. So what happens if I put a bunch more input in? Let's see. All right. So let's do that again. So now we've just got 61s across the board. Let's print out some more. So we've got a bunch of 61s. What about base pointer? Oh my god, so that is there. How about if we print out some memory from our base pointer? And we can see we've got, past the base pointer, we've got 8, 9, 10 bytes of A's. So we've trashed some of our stuff. We've trashed some of our bookkeeping that we've got on the board on the far right. And we've trashed our return address. So I guess it stands to reason that this program should crash, except in this case, in this example, we never actually return from this main. We call our exit. But we'll see more examples of this later. So what can we do? What can we do with this? Let's see. So I've noticed a thing right up here. We've got name and we've got a second buffer that is 14 bytes long. Because of the order that these are stored in memory, name should be stored before this the second buffer. And I've just written A's over them all. So if we continue, I reckon that for the name and the second variable in the string, it's going to print out a bunch of A's, and it did. So we overwrote both strings, which is kind of interesting. But let's see. I think we can do a little bit better. So we know that this first buffer is 10 bytes long. So we also know a little bit about how printf works, right? It'll print up until a null byte. So if I put in my name and then I put in a null byte, and then I put in a little bit of padding so that I can get to the beginning of this second buffer, maybe I could have it output cleanly, something neat, something that it wasn't designed to do. So let's try doing that. Does that sound reasonable?
Nope.
Nope. Let's do this. Nope. Nope. Let's try writing this file first. Whoops. Nope. I'm in the weeds, man. All right. So what did we decide we wanted to do? Let's have it print my name, and then let's print a null byte. Then what can we do? So how many bytes have we used up? 1, 2, 3, 4, 5, 6, and then 7 is the null byte. So let's print a couple more to fill up the buffer. Let's see. Let's just print. It doesn't matter what we put here. Let's put our A's in again so we can identify them easily. So 7, 8, 9, 10. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's probably going to be, I think 4 is going to be enough. We'll see. And then if I put in a second string right here, and as long as I null terminate it properly, we should get it printing out. So let's change this. Yeah. Wait a second, we can't go over this buffer or we might crash. Maybe not, screw it. We'll do it live. It'll be fine. All right. So what happens if we do this? Oh man. So we're pretty close. We got my name, it stopped printing, we found the null byte, and then it encountered a bunch of A's in memory, and then it encountered the misec Jackson that we put in. Let's put this over here. All right. So there's the name, there's our A's, there's misec Jackson, which is where we are. But we've got one A in the output right about there. So that means I put in too many. So let's fix it. Let's put in one fewer. Oh, thank you, PyFlakes. Thank you, PyMode. And there we go. So let's have a look and see how this works. Let's do the same thing. All right. Whoops. Seems reasonable. Let's see. not sure how to do this. Let's do this. All right. So now if we look at memory again, we should see, oh, we have a bunch of trash because I haven't moved stuff over. Oh my god, this is crazy. All right. So we're looking at the same region of memory we were looking at before. Let's see if we can see anything that we recognize. So I see some A's. I see 1A, and I see 2 A's, and I see 3 A's right there. That's pretty interesting. And I'm going to assume right here that this is my name, whatever the hell that is. There's a 61. I got an A, right? And then after that, we don't have arrays anymore. We've got the rest of the trash that we put in. Let's make sure that we didn't break the base pointer this time. All right, so I don't see any 61s here. It looks like we didn't go too far. We didn't trash anything. And this time, we get a cool string printed, which is not what we wrote in the original source code, right? Let's have a look at this. That's what I want. So we overwrote. Where we overwrite? There it is. We overwrote misec Lansing with misec Jackson, which is a terrible thing to do. But we are in misec Jackson, and tomorrow is misec Lansing. You know, don't forget about that. So if I was to do this presentation tomorrow at 7 at 300 West Washington, something, downtown, then, you know, I'd obviously do it the other way around. All right, well, that was kind of cool, but I don't think it was that cool. So, luckily, it was fine. You were fine with it? You were fine with it. I see. Actually, let's get rid of this. We don't need this anymore. All right. So we have a second example. Maybe we can do a similar thing. Let's look. Oh my god. All right. Let's do the same thing. Let's look at main. Okay. This is a lot shorter. This is a lot more manageable. But I see we've got a bunch of function calls. And the first function we call is called input. That sounds promising. All right. So we've got another call to gets. We're going to get some more input from standard in from the keyboard. We're going to return. And when we return, we're going to go back to, well, right here, right? We're going to have this, when we return from this function, it's going to go right down here to this second function, and it's going to call this. I don't know what it does. Let's find out. Okay, let's do this again. All right. Well, that was boring. I hated it. What about, let's see. What if we do our trick again? What if we do our trick with a bunch of A's? Looks like we crashed it. That's no good. Okay, so we've changed the behavior by changing our input. We've broken something, and at the moment, I know that something similar is probably going on. We've probably got a stack that's had a buffer allocated for us to type something into, and apparently that much input has trashed everything, and when it tried to return to main, it tried to return to, we can see right here, this is what the base pointer was. This is what the base pointer, this is where the base pointer was when we returned, and it's full of A's, and so by my logic, I think we've trashed the return address, which is kind of cool, but you know, we've got denial of service, we've crashed the program, but can we do something different? So what else is there to do here? Let's see if this thing has any other functions, and the answer is it has a bunch. So let me scroll up a bunch. Let's scroll up a bunch. So with this GDB command, we asked it to tell us the names of all of the functions that it knows about from this file. And there's a lot of boilerplate. Find at least an entry for main and an entry for all of the locals. All of the functions that are in scope that were compiled. So there's our main. Hey, look at that. And I recognize this, and I recognize that. This is input. This is the function afterwards. Don't know what it did. Don't know what input did. You know. And there's our main. This is kind of interesting right here, though. I didn't see this when we disassembled main. There's no call to this function. It's like there's some sort of hidden functionality here that maybe the person who wrote the program doesn't want us to see. So I wonder if there's a way we could call this function, right? This function has an address. It's in the program. If we could perhaps, we've already established that we can overwrite the return address. When we try to return, when we put in our trash, it crashes because we didn't give it a valid address. but maybe we could put in just enough input and then a different address to return to it. The only question is, how do we figure out what the address of that hidden function is? And the answer is we can find out here by naming it. And we can see that the address that we would want to jump to is on this line right over here. This is the address in the text section of the program, in the code section, where this starts. So if we can get the instruction pointer, which keeps track of which instruction we're going to next, if we can get the instruction pointer to store this value that's right here, we should be able to jump to this code and see what it does. All right, so how are we going to do that? We need to figure out how big that buffer is. And we could guess and check, because we put in a small input and it worked fine, didn't crash. We put in a big input and it crashed. So how do we figure out how far to go? So we remember from earlier we saw a function called input. It stands to reason that that is the function that is dealing with the input. So let's look at it. Okay, so we've got our call to gets, and this time we notice right here is where it is advancing. Wait a second. Here is where it is advancing the stack pointer. So this is the beginning of our function. This right here corresponds to earlier on when we had the stack pointer and the base pointer pointing in the same place, and then we moved the stack pointer down as we allocated our buffer. That's how you allocate memory, right? You just say, you take the stack pointer, the counter of where we've got to in memory, and just move it down. Look at all the space we got. And that's basically what the computer does. It says, you now have this space. So how much space did it give it? It gave it 20, oh man, hex 28 bytes of space. So maybe the buffer is exactly that big, maybe the buffer is a little bit smaller, but we know we're in about the right ballpark. So watch that. That's 40 bytes, right? Everyone? Anyone? Ish?
Sure.
Yeah, let's go with that. If someone could fact check my math, that would be wonderful. So let's do the same thing we did before. Let's put something we'll recognize in memory and see if we can see it. Let's see. So let's put a breakpoint. Let's see. So there's our call to our function that gets input. So let's put a breakpoint at the instruction after it, which is on that leave line. Let's run it. Let's put in a bunch of A's. Let's do it again. This is great fun. This is a little guess and checky, but let's see what happens in a minute. So let's do the same thing we did before and examine the stack. Well, we see our bunch of 61s that we were looking for. So from our calculation up there, from our calculation before of how much it moved the stack pointer down from the base pointer, we should be able to figure out approximately how much stack space we have. So let's see where the base pointer is pointing at. And I'm just going to talk about the last 2 bytes. We know the base pointer is pointing at F688 because it says so right here. Where's F68? F68 is on this line. So all of this stuff right here is unnecessary. So we have overwritten a lot right here because I can see 61s are going way down. So where is the base pointer? 688. So this is 680, this is 684, this is 688. So the base pointer is pointing right here. So this should be our saved frame pointer. This one right here should be our return address. Let's check. If we run it again and we give it a normal amount of input and we do the same thing, right here we should be able to see. So this is where I think the base pointer is pointing, right around here. And I think that this little area right here, these 4 bytes, should contain the address to return to after the function's done. So let's check. Oh my god. So let's print 2 words from our base pointer, and we should see our 698 and our 8F3A. Looks like it to me. So this is our return address. This is the address the program's going to jump to after we get out of this function. Where should that be? This was called from main, so this should be an address in main, right? Oh my god, there it is right there. So this is the address of this crazy function. I don't know what this crazy function does, but it wasn't very interesting last time. It told us there was nothing to see here, so I'm not satisfied with that. So we need to change this address to the address of that extra function that we can see in GDB, but is not being called. Excuse me, have a drink. All right. So the approach is very obvious. We put in a bunch of trash until we get to that critical part. And then we put in the address that we want, which, as a reminder, right here, that address we want to say 8F11 instead of 8F3A. So how do we figure out how much that is, right? We know from earlier what we can do. We can do some math using the numbers from the disassembly that we saw earlier, or we can make it even plainer and just count, right? So here is my first A, right in this word. And here is our return address. So that's 4, that's 8, that's 16, that's 12, that's 16. That's 20 bytes of A's, and then the following 4 bytes 20 through 24, are going to be our return address. So if we put 20 bytes of trash, and then we put exactly the right address that we want, which we already know, because it's right there, we should be able to make this work. So let's do that. Whoops, let's not break everything. Whoops, why do I keep doing this today? Nope, yeah. All right. So we've got an import at the top. We'll explain this shortly. First of all, let's do what we came here to do. Let's put our 20 bytes of trash. And it doesn't really matter. I don't know what this program uses the input for. Maybe it matters what we put in here. Maybe it doesn't. I am just going to put in, I don't know. Let's just put in a bunch of null bytes. So there's our 20 bytes. The next 4 bytes should contain our address. The address of our function that we want to call that otherwise would not run. And here is where it gets a little more complicated. This is always the thing with computers, right? Oh, it works, it's easy, it works like this. Oh, but wait, when you do it for real, you've got to do this one more thing. This one more thing is always super opaque, and everyone just says, you just do it how I have it written down in this wiki. And no one understands why the hell it works. But, I did the same thing, and I didn't understand how it works. So this next part is a little bit of the Hollywood magic. When we store the address, when we store the return address on the stack, we don't store it in the normal way. We store the bytes backwards. We store the bytes in little endian format, as is the want of the x86 processor. This is something that is going to change based on your architecture, based on your compiler, maybe based on your operating system. So we have to be aware of this, otherwise it's going to read our return address wrong. And now that I've said that, we could see an example, but I don't want to take too much time. So we're going to wave our Hollywood magic wand right here. Let's see. And we're going to use a Python function that will do this for us. So we're going to say to this Python function that we want to print this address in little endian format in unsigned integer. That's 08048. What did we say that function address was? Let's say it was that, because I think that's what it was. And again, the only reason we do this pack is to have Python automatically reformat this address for us so that the computer gets what it expects. And we'll see this again shortly. So let's get out of there. Let's do the same thing again. Nope. Let's try this again. Yeah. All right, so we've just got our output and put it in a file just so it's easy to work with in GDB. Because I can't remember how to use bash when I'm under pressure, basically. All right. Are we still in the same place? Yeah, we are. All right. Let's check that I put that address in right. F11. There it is. OK. So let's do the same thing we did earlier and break right after that input, which is right there. All right, so let's look at the memory, as we are wont to do. OK, so this time we put in a bunch of, the trash that I put in was just a bunch of null bytes, right? In C, I'm a C programmer at heart, we like null bytes, right? Maybe, I don't know. So here are a bunch of zeros, that looks familiar. All right, so we know our buffer begins here, we know our buffer ends right about there, so that's 16, 20. This is the end of our buffer, and this would be our saved frame pointer that we don't really care about right now. But this is the return address, and we'll notice this has changed from what we had earlier. And I will show you, I think I can actually show you. If we change this a little bit. OK, so this display is this byte and this byte that was all smushed together up here, and each byte has been separated out here. So this is where the base point is pointing. We know the first 4 right here are zeros because that's what we put in here. These last 4 bytes are our return address. And our return address is 0804-8F11. So 0804-8F. Wait a second. Okay, so this is the backwards little endian thing that I was talking about. We can see exactly how it's laid out in memory. On the top display here, GDB is doing a little bit of Hollywood magic behind the scenes and reformatting everything for us so that it looks nice. It's showing us words at once, which is what this little W right here, show us bytes formatted, show us words, show us 32 words formatted in hex. Right here, show us 8 bytes, which is 4 bytes, 8 bytes, just these two. We could say 32, it doesn't matter. And instead of showing us whole words, show us bytes as hex. And that's what it did. It showed us the bytes, the raw bytes output, instead of smushing it all together. So here we can see the little endian stuff at work. This is the beginning of the return address. So 0804-8F11, that's what we put in, which is why we have to use that pack. So right now, fingers crossed, if we carry on, we should return to this function that is not otherwise called. So where are we? We're right here. So let's step one by one. Here we go. Here we're going to return. And where are we right here? So luckily GDB has labeled this with the function, and here's F11. Exactly what we thought happened. We returned to a different function. And we should have returned right here. This function, lancing, is not called. It's not called here. Right? It's real, man. It's real. So let's just let it carry on, because I don't know what this function does. All right. Pretty good. Looks good to me. So we got some different output. This is kind of neat. And then we exited normally. We didn't even break the program. I'm so excited. So let's prove to ourselves that this really works. Outside the debugger, because sometimes the debugger can make things a little muddy. The debugger changes the environment. Sometimes things like this don't work quite the same. And in our scenario of writing an exploit, we definitely want our exploit to be able to work outside of the debugger, somewhat obviously. I don't even care if the exploit doesn't work properly inside the debugger. I care that it works outside all the time, every time. So we've checked. So let's compare it once more just to convince ourselves that we've changed something. If we just give this a bunch of input, it's going to do that. And if we give it the right input, it can jump to this second function that is not called normally. And we can see, did we see this before? Right here. So here's the source code. This is a little bit of a cheat, right? Normally you don't have access to this. So here's our main, here's our input, here's our crazy function, then it returns. And here is this, whoops, whoa. Easy now. So here is the function that was compiled, because we didn't turn on any optimizations in GCC when I compiled this. Normally, if a function is not called, it's often trimmed out and you don't get it. But I turned that off so that it was compiled and accessible if you know where to look. Kind of technique though, right? We've taken advantage of where things are on the stack. We've taken advantage of how memory is laid out. Let's see. So that's kind of cool, I guess. We made this program output something. We made this program do something that it wasn't originally intended to do, judging by main. But still, we're only doing things that was programmed, that were programmed originally by the programmer. We haven't introduced any sort of arbitrary functionality except for the crash, which was pretty cool. I like crashing stuff. Wouldn't it be nice if we could, instead of maybe jumping to a different return function, how about we jump to our own function? So this is we're starting to get into the concept of shellcode. Shellcode is kind of a loaded term. People throw it around a lot. Its meaning is very simple. It is code that spawns a shell, which is kind of a nice thing to have in certain circumstances. You know, when you boot your computer up, you get a shell. I got a shell right here. No big deal. But what if it's a computer that I don't normally have access to? It might be nice to be able to get a shell, especially if we're running a program. Maybe we can't quit it. Maybe we don't have permission. Who knows? But if we can craft some input that could perhaps spawn a shell, I think that'd be pretty neat. So I'm sure that you've all read, and if you haven't, you probably should. There's an article online called Smashing the Stack for Fun and Profit. I encourage you to look it up, and it explains how to do all of this stuff. So the technique that we're going to use is detailed in Smashing the Stack. and detail everywhere else. The concept of jumping to one's own shellcode is very common. So we're going to take advantage of a buffer in a third example program, much like what we've done so far, except at the beginning of the buffer we're going to put some arbitrary code. We're going to put some shellcode that we wrote and we compiled and then we dumped, so we got the raw bytes. It stands to reason, I mean, that's what's in the program file, right? Just bytes of compiled code. So it stands to reason that if we could put some bytes of other compiled code that someone else compiled somewhere else into the buffer of whatever program, and then we could trick that program into jumping not to the address of some function inside it, but maybe jumping into the middle of the buffer, it stands to reason that it should execute our arbitrary code and maybe get ourselves a shell. So to keep the time down, this is not going to be a shellcode writing tutorial. I've written some shellcode already. We're going to see it. But what I would do, and what you should do if you're interested in trying to write your own shellcode, you just want to write a very simple program that executes a system call, runs a shell. As long as you know where the shell is located on the system that you are dealing with, which is going to be in the Windows folder, cmd.exe, or in bin bash, bin sh, bin zsh, whatever you want. Bin sh on Linux is pretty usually aliased to something good at least. So it's a pretty safe bet. So to write one's own shellcode, you'd write a small C program that executes the shell, and you'd compile it, and you'd dump the bytes out. And there you go, you got your shellcode. And a lot of people like to make an entertaining game out of writing very short shellcode. Shellcode that is the shortest in length, then you can fit it into more buffers, right? Okay, so let's have a look at our third demo program. Nope, let's not do that. Well, let's not do that. Let's try to remember what I'm supposed to be doing. All right. So right here. All right. So we've got our main function. I can see we have some jumps in here. We have a call to the right thing. This function call right here jumps out at me. The name of this function looks pretty interesting. But we've already done this, right? This is boring. Yeah. All right. So in here we have a vulnerable function that has this program actually takes a command line argument, and we will see that shortly. But the interesting parts are right here. So we're doing the same thing. We're taking the base pointer and subtracting a bunch from it. We're doing that up here. I'm sorry. We're doing that right here. We're subtracting a bunch, and we are storing the result in the stack pointer. So right here we copy the base pointer into the stack pointer. Right here we subtract a bunch from the stack pointer. Now we've allocated some space on the stack. And that is a fair bit of space, right? It's 8 times 16 plus 8, which I can't do in my head under pressure. So we have a buffer. I know this function is vulnerable. Let's see if we can prove it. So let's do our test. Let's do our sort of crappy little test and see what happens. So I know I'm going to have to put in a bunch of stuff. Let's try actually doing it properly. Yeah, let's see what happens. And, well, that wasn't very good. No. I can't remember how to use GDB in the heat of the moment. That's the question here. Okay, so this right here should look very familiar. Cannot access memory at address AAAA. We've already overwritten the buffer, right? All right, well, that's fine, I guess. Let's have a look at this one more time. Okay, so let's do the same thing we did before. We need to look at the memory, so we need to stop it while it's running. Let's see, where are we going to put it? I am going to put it right at the leave, I think. Yeah, let's put in a bunch of A's so we can identify it. All right. Okay, well that's kind of interesting. I didn't see a whole lot of much in there. Let's look at where our base pointer is. So it looks like we have not screwed up our base pointer yet. Our base pointer is still pointing at 8F48, which is the line right after vulnerable. Is that right? Did I just lie? Did we actually? Oh my god, it's totally not. It's totally pointing somewhere else. Where are we? Have I become lost? Oh my god, we've already called leave, so we've already popped the no, we've already popped stuff off the stack. We broke too late. So let's try this again. Yeah, let's put in another breakpoint. Nope, nope, nope. There we go. EFB. Let's do this. All right. We having fun yet? Did I just...
That wasn't shaky.
Nope. Wasn't shady at all. So if we continue right now, we'll hit the next breakpoint on the next line because we've already left it turned on. But I don't care. So let's do the same thing. 8F48. Is that what we had? Whoops. 8F4. Hey, look at that. It's our return address when we don't break the demo. Oh my god. Okay. Let's see if we can identify where... Whoops. Okay. So we can see our A's, right? And the reason that we didn't see this before is because we'd already munged this ESP before. We'd gone too far. So we see our A's. So we can do the same thing we did before and figure out exactly where this return address is, right? What address was this again? All right. 288. So this is the extent of the stack. Our buffer is right here with all of our A's in, and it seems like we've got some more space, right? Our base pointer is pointing at 288, so 29. We haven't gone far enough. If we print some more, 2A, 2A4. Oh man, there it is. So this is where our base pointer is pointing to. This is the saved frame pointer, and this is our return address. And we can prove that to ourselves in much the same way we did before by printing just 2 words. There we go. So we have got from here the beginning of where it reads the argument from, the beginning of the buffer where the argument is stored in memory, to here, which is our return address. So we need to put in the same thing we did before, right? We need to put in a bunch of trash until we get here, and we need to overwrite the return address. But in this case, we don't want to overwrite the return address with the address of some function that's in the program already. What we want to do is, instead of putting a bunch of trash in this buffer, we want to put some code in this buffer up until some amount of space. As long as we don't overrun the space that we have. So we have, let's see, 60, 30, we have 64, we have a bunch of bytes, right? We have 64, we have, oh my god, this is too complicated. We have like 96 bytes of space-ish, right? About 100 bytes of space. So our code can't be too long. Luckily, code that just spawns a shell, as we will see, usually, oh, the screen's gone off. Oh my god, I'm freaking out. Is usually pretty short, so we should have enough space to play with. Okay, so let's see. Let's see. Okay, so let's output our shellcode that we have pre-written, and let's output some padding, and see if we can see it in memory. It's a pretty good start, I think. Okay. Okay. Well, let's look at our shellcode first, because I feel like that's a little hand-wavy. All right. So this shellcode is very short. We will see what this disassembles to later. So this is a C program that's been written, compiled, dumped, put in a Python string. Don't care about it. We'll disassemble it later and see what it does, right? That's how I'd see what it does. I'd load it into a program and disassemble it. Or load it into object dump or something. Okay, so what's our approach? First of all, that seems pretty reasonable, right? So we're outputting that string from the other Python file that we've got. It's just those bytes. We don't have to it's already been pre-fixed. Everything is in the right order. We don't have to pack it. We don't have to do anything strange. So let's put in a bunch of trash. Let's put in our traditional A again. Let's see. We saw about 100 bytes of space, but I wasn't counting. Were you counting, Kyle? No. Good. All right. So let's do that. Let's just put an 80 for now. And we know that after this we're going to have to pack the return address in little endian format, but we don't know what the return address is right now. So let's go with that. That's probably pretty good for now. Let's see. All right. So in this program, I decided to make it take command line arguments. So let's do that. We're going to run this slightly differently, but it's probably going to be fine. Well, let's do it properly. Okay. Let's see where we were. All right, let's put our breakpoint back in. Yeah, let's where are we? B. Okay. So we've already specified our arguments, so we can just say run this time. Let's look at the memory. We like doing that, right? I like doing that. Okay. So the buffer starts at the same place that it did last time. So I happen to know that the shellcode that we have begins with the bytes 6A and 0B, which we can see right here. So this is the beginning of our shellcode. Let's check. Let's move this over a little bit. Oh my god, let's move this over a little more. So we can see some stuff. Yeah. Look at that. 6A, 0B. I'm pretty convinced that is the beginning of our buffer, and we have emitted it correctly. And the only reason that I use Python was just for simplicity, for convenience. Nothing special about the way this is being emitted to the to standard in or to an argument and passed in to the program. So we can see we have a bunch of shellcode. It's not that long, so that seems pretty reasonable to me. And here are our A's that we put in. So we've got, let's see, that's 16 bytes. That's 20 bytes of shellcode. Yeah, 20 bytes right here. So 21, 22, 23 bytes. See that 61? That's our first A. And here are a bunch of other A's. And I think the return address is somewhere around here, right? Let's check. 48? Oh, there it is, right there. Okay, so we were actually reasonably close already.
You just need 5 more, don't you?
5 more what?
A's.
5 more A's. So 1 more A plus 4 more A's. This is our saved stack pointer. This is our return address, which is what we want to overwrite. So we need 4, 5, because there's a 0 right there, and then another 4. Close enough. Okay, so let's modify our solution. Oh my god. All right. How many more did we say? 9? All right. So if we emit this many A's, we will fill the buffer up to this byte right here, which is our base pointer plus 4 bytes. What am I doing? 2 words from the base pointer. There it is. There's our 2C8 and our F48. There's our 2C8. There's our F48. So this is the one we need to overwrite. But what do we overwrite it with? We've got to figure out exactly where this buffer lives in memory now. And it seems a little weird to be jumping in at the middle of a variable, but we've already filled the variable with code. So we'll see what happens. How do we figure out where that buffer is, though? You know, it doesn't really give us a lot of information here. We can see that we are allocating a bunch of space on the stack, but we could do some math and subtract this number from the base pointer to get where the stack pointer is. It's just the stack pointer, right? We know that our buffer starts somewhere along there, but we don't know how big this buffer is because we haven't looked at the source code. And it's kind of tough to, without examining exactly where it is in memory and proving to ourselves where it is, it's kind of tough. You'd have to guess, I think, a little bit. But luckily, right up here, we know exactly where it starts, which is, this is our first A, did we decide? So, let's see, that would be 253 is where it starts. Right, 250, oh, nope, that's not, is that true? 253, 23. Oh, no! So, the end, say that again, someone?
No, you're right. That's right. 2, whatever, 2.
Right, so this is our first A, but I forgot something. I'm glad that somebody said something, because we got our shellcode, and we know our shellcode starts right there, which is 2, 3, 4, 234, 238, 239, 23A, 23B, 23C, right? So it stands to reason that the beginning of this buffer is at address BFFEE23C, right? This byte right here is 23C. Let's prove that to ourselves. What did I say? Oh my god, what am I doing? 23C, and we should see that byte right there, which begins with 6A0B, which is the beginning of our shellcode. Oh my god, we're getting closer. We are getting closer. Okay, so let's add our address in. Let's pack it in a little endian format because we know we've got to do that. B, M, M, E, E. What did we say? 23C?
Mm-hmm.
So I'm pretty confident that that's going to work. So let's find out. You know what? Screw it. Let's just run this thing. What am I doing? Oh my god! So our program didn't exit cleanly. It didn't crash. It executed our shellcode, right? We got our shell! Look at this, look at this, look at this. Oh my god, I can do bash commands. Ah, so good. But why did we get a root shell? I'm not a root user, right? What about this? Let's see. Is that, oh man. Okay. So I can't do some things as my normal user. So I think this is kind of cool. So this particular program was compiled with certain options, or rather the file was modified with certain options. This file is owned by root, and it has the sticky bit set so that it will run as the owner, not as the person who ran it, which is a little unusual. But it's kind of cool to find a vulnerability like this in a program like that, because it means as long as you have permission to run the file, which we do, it will run with the effective permissions of root, and any process that is spawned from this program will also run as root. And this program normally doesn't spawn a process, right? Did we run it? Whoa, 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 whoa. I don't know, nothing good. Yeah, nothing good, doesn't do anything. That sucks. But, you know, we made it spawn a shell. Let's do that again. Let's prove to ourselves that it actually works. Okay, well, that's probably fine. Oh my god! So we accessed a restricted file that normally we would not be able to see as the normal user. We didn't jump to any code that was already in the program. We inserted our own code, and we fixed the return address so that the program returned to the middle of its own variable, and we changed the control flow into our own code that we wrote and inserted. We could insert different code. We could insert code that runs a different program, but in this case I decided to insert code that ran a shell, which is why it's called shellcode. All right. That's... Hi, Kai. So I think that's kind of cool, and we saw how you would try to do this. You know, the kind of investigation that we did with the debugger is something that I wish I'd been shown when I first started programming, at least. People say, oh, you just put stuff in a buffer and then you get a shell. So how does that work? So I hope that I have illuminated the mysterious depths a little bit for you today, and I hope that you got something out of this. And that's all I got. Yes! Yes! Questions in the back.
Do you recommend any type of debugger when you're doing this? Is there any certain kind you actually use? I know you use built-in, but...
The debugger that I would recommend is one that can show you the registers of your CPU, the one that can show you arbitrary areas of memory, and the one that can automatically disassemble areas of memory or areas of the program for you. So as long as you can see the disassembly, as long as you can see where variables live, and as long as you can see the whole stack, not just what, well, being able to just name a variable and dump that variable is kind of nice, but it's also nice to be able to see bytes outside of that variable. So I wouldn't recommend any debugger in particular. They all do that, I think. GDB is pretty good. On Windows, you could use Visual Studio's built-in debugger. You could use WinDBG, you could use WinBag. You could use whatever the hell you want. So, not really. The one you're most comfortable with. Any other questions? All right, let's go drinking. Oh, no! You, sir!
You know, you hear about ASLR and depth and those
Yes.
kinds of things in Windows. Is this what they're effectively trying to prevent you from doing?
Yes, I didn't even mention that. I didn't even get to that. I was, maybe we can do another demo of it another time. This environment is a little bit Hollywood magicked, as I said earlier. I have turned off a bunch of security features. We have turned off data execution prevention, which is a function of process of hardware and software that prevents you from running code in the space of the variables in the stack. If we try to do what we did and jump to code in the stack, won't work with this security feature turned on. Similarly, ASLR, address space layout randomization, will mean that these addresses that we put in here, you could still guess at addresses, you could still insert addresses, maybe you can still overwrite the return address, but every time you run the program, the address that you need to jump to will be different, because inside of the address space that is allocated for your program, the actual program data, the stack, will be at different places every time you run it. The operating system will take care of that. In this case, we have disabled that. There are ways around both of these things. if people are interested, we could do another demo. We could get around both of these things. But not right now. There are techniques that would bypass them both. Something we did not get into is the infamous nopsled, where you would take you would have your code that you want to run, but you don't know exactly where to return to. We could see in the debugger exactly where we needed to return to. With Aslr, we need to do some guessing. But luckily there's an instruction that when executed on the x86 processor will just do nothing and advance the instruction pointer to the next address. And just keep going and keep going and keep going. The no-op. Every CPU has a no-op, I think. Probably just lied. Who knows? So if we could prepend our shellcode with a bunch of no-ops, it doesn't really matter where that buffer begins, where we return to. As long as we're in the right ballpark, it'll hit a no-op and then it'll slide to the shellcode and execute shellcode. Similarly, with data execution prevention, we can't execute any code that is on the stack, but we can execute code that's elsewhere. When we looked at the functions earlier, we saw there was a bunch of code that was accessible. There's a bunch of library functions. The technique to get around DEP is to construct what are called gadgets, that is little slices of code that are already executable, and jump to them in such a way that causes the behavior that you want, whatever that is. So these things can be overcome. Here, for simplicity, and so we could prove to ourselves exactly what was going on by examining memory and have it not be crazy and confusing, turn some of those things off, sure.
On your corporate laptop then?
Obviously. Don't know what you're talking about, sir. Next question. Yes?
Is Whoopsie an actual default account on Ubuntu, or is that something you did?
Google. You tell me. Sorry. Ubuntu's crazy. I don't know. Any other questions, or are we free for the night? All right. Kyle? Wait a second. Don't look at me. Don't you do anything to my
it's all
machine.
magic back here.
Don't you do anything to my machine, man.
Well, thank you very much for coming. I don't know if anybody's heading to Nightlight, but if you are, I might be hanging out there.
Tomorrow. What's happening tomorrow?
Tomorrow is also misec lancing, which we mentioned at the start of the meeting.
We should mention it again.
And then we heard it a few times during the presentation. Very surprising. Address and everything.
I don't know what you're talking about.
Yeah, it's amazing. For our next misec meeting, we'll actually be potentially having an FBI agent come out and talk a little bit about the cybersecurity work that he has to do.
That's going to scare us all.
So if you're a little scared, I would totally show up. He's a nice guy. So that's all I got for today. So see you.